This section focuses on relative frequency, the idea that probability can be estimated based on a lot of trials or a lot of repeats of behavior. And we're also going to talk about simulation. Chance behavior is unpredictable in the short run, and even though we know the probability of something what it should be, it really only has a predictable pattern in the long run. So as we have experienced with the simulator and the simulator with the flipping coins with a small number of trials, there's a lot of erratic behavior, and it might be all erratic up here, or it might be like that, or it might be all down there. But in the long run, it's going to approach a single value. In the case of flipping a head or a tail, it's going to be a 0.5. Every probability has a number between 0 and 1. And that's an important piece, whether we're talking about probability as a model from a sample set or for looking at this idea of relative frequency. So when we talk about randomness, there's definitely some things that we have problems as humans connecting the intellectual truth and what we tend to feel has to be true intuitively. We know that the law of large numbers says in the long run we can have a prediction with relative frequency about what that single value of probability is, but in the short run we really can't predict it. And the other idea is the law of averages, which is a myth. If you have had 5 tails in a row, the next one still has the same probability of getting a tails and a head. It's not going to even out in the short run. It's going to even out in the long run. So the law of averages is not something that we need to. It's not a thing. It's an incorrect assumption. Whenever we're making a simulation, we're going to follow the 4-step plan that we talk about whenever we're creating a plan for answering a statistical question. Simulation is the same thing. We look at our question of interest. We describe how the chance device is going to imitate one repetition of the process. This is a big one. What are you going to record at the end of each repetition? And then, as many repetitions of the simulation, less than 60 is just not okay. It has to be more than 60, better to have 100, better to have 1,000. And then once you have your simulation results, you're going to go ahead and answer the question. And we're going to do quite a few of these in class, so you'll get practice about this. I'm going to give you a real quick explanation of one. The problem that we're trying to figure out is this NASCAR fan wants to get all 5 of the driver's cards that are in the boxes of cereal. It takes her 23 boxes to get a set of cards, should she be surprised. And so they're assuming that the 5 cards are equally distributed into the boxes. Then we'll see if we can figure out if that's weird or not. So what the decision was, we're going to use technology. So we're going to number each of the racers, and then you're going to use random integers 1 to 5 to simulate buying 1 box of cereal. They want full sets of cards. So we keep pressing enter until we get 5 of the labels from 1 to 5. If you get a repeat in this case, it just means another box of cereal that you have to eat, but you didn't get the card that you wanted. So in this particular case, we're going to write down the number of boxes it took us to get our full set of cards. That's what we're recording each time. So here are the results of 5 of the 50 simulations that were done, 50 repetitions of the simulation. And so this first time, they got a 3 and then the 5 and a 2 and a 1. They almost got all of them, and then it took 5 more boxes before they got all 5 cards, a 1, a 2, a 3, a 4, and a 5. They continued this process, and they did it 50 times, marking each time each number of boxes that it took on the dot plot. And she wanted to know how weird it was that it took her 23 boxes. Well, here is 23, and out of the 50, 0 of them took 23. So that's a 0% chance. And when we're talking about statistically significant, 0% chance is as significant as it can get. So here, 0% of the time it occurred that it took 23 or more. So we can, she definitely should be surprised. That doesn't happen very often. I'm also going to go over the basic probability rules in this video as well. We'll get into the nitty-gritty of it in class as well as the symbolization. So this is just the basic ideas of probability. So in this particular one, we're just gonna talk about the first two objectives here, describing a probability model with a sample space and individual probabilities of events, and then the basic probability rules. And then we'll get into more complicated ones when we're talking about conditional probability and such as that later. Sometimes the only way that we can to come up with a probability is to run simulations or to try something out over and over and over again until we think we're approaching the true thing, such as someone's batting average. There's not a set of things we can write down and figure out the probability of it happening from that. But there are a lot of things in chance that we can. And so we can start with a sample space, which is a list of all the possible outcomes, and then we can go ahead and figure out the probability for each outcome. And we're going to do quite a bit of that as well. So the first part of building a probability model is to create a sample space. In this case, it's the sample space where the list includes pictures. That's not necessary, but in this case it is helpful. And it gives you all of the possible outcomes of rolling 2 dice. And for example, you could get a 1 or a 1, or you could get a 6 with the orange and a 2 with the white. You could also get a 2 with the orange and a 6 with a white. They'd have the same sum, but they're 2 separate possibilities. And so there's 36 possible things that can happen when you roll 2 dice. And since the dice are fair, each outcome is equally likely. So each of the different pairs is probability. There's a 1 out of 36 chance that each of those will occur. So once you have your sample space, you can go ahead and look at certain things that you would like to find the probability of, and we call those things we're trying to find, or the collection of outcomes, an event, and that event is a subset of the sample space, and we normally talk about them in terms of event A, event B, event C, but you can also define the event ahead of time, or you can define it in the parentheses. So we can say, what's the probability of A if A is the sum of 5, or we can just write it as what is the probability of the sum of 5. And in the sample space from the previous page, there's 36 possible outcomes. Of those, there are 4 that will get you a sum of 5. And so here we are, the probability of A is 4 out of 36. And we can write that in that form. We can simplify the fraction, or we can go ahead and find in this case it repeats, and we can say it's about 11%. I am going to ask you every time to label where you get your numbers. So this would be 4 ways to get a 5 out of 36 possible outcomes. By the way, here we're talking about B as being the sum of not 5, so that's all of the other possibilities. So there's 2 ways to do that. You can look at all the things that are not 5, or this is called the complement of A. So the complement of A would be 1 minus A. So you'd go ahead and 1 minus 4 out of 36. Because if you add A and B together, you get a total of probability of 1, or 100% chance that either you're going to get a sum of 5 or not a sum of 5. That's all of them. So there are a couple of basic rules of probability. One is any event, the chance of it occurring has to be a number between 0 and 1, or if you're talking about probability as a percent, between 0 and 100%. When we look at all the things that are possible in the probability model that we're looking at, when we add all those probabilities together, it will be exactly 1. That's the 100% that we're talking about here. And if the outcomes in the sample space are equally likely, the probability that event A occurs is the number of outcomes corresponding to event A, and then the number of total outcomes in the sample space. And the complement then is if the event is not going to occur, it's just 1 minus that event. So 1 minus A would get you B if they are the opposite. If two events have no outcomes in common, then the probability of one or the other happening is just adding them together. So if B and A are not are what called mutually exclusive, then we just said the probability of one or the other happening is just adding them together. And we're going to talk more about mutually exclusive in class. It just means two things that can never occur at the same time. We're going to spend a lot of time in the symbolic form, and so we're going to do this in class. But basically, those 5 rules fit into these symbols. Probability has between 0 and 1, sample space, the probability of everything in the sample space added together is going to equal a total of exactly 1. And this is how we find the basics of this is how we find the ratio that we use to create a probability, and then the complement rule. And then for mutually exclusive events, if we want A or B, we just add them together. So here we go once again. We have just dealt with those, and then we're going to deal with more complicated chance processes, including conditional probability later.